now we will see about the some important topic in this strain energy due to the torsion in the unit 4. Before getting into this topic, we have to recollect some of these things. What are the types of loads are there? Okay, point load, UDL. So these are according to the application. So then according to the, if you are pulling, what is the name of that load? Opposite pulling, that is a tensile load. If it is opposite pushes, it's a compressive load. If I am applying the forces tangential, it is a shear load. So if I am coupled, it is the torsion. Okay, so according to the application we are dealing. So what are the types of stresses? What is the meaning of stress first? Stress is nothing but force per unit area. Okay, what is the strain? Dimension by torsional dimension. So according to the type of load, the stresses will be varied. So if it is the shear, if you are applying the shear load, it will be a shear stress. Okay, or if it is a what is the shear strain change in dimension by torsional dimension. Okay, so now according to the load, the stresses will be varied. And what are the elastic modulus are there? N modulus, rigidity modulus, shear. So what is the meaning of shear modulus? Shear stress by shear stress. Relation between shear stress by shear stress. So here that's what we are going to be using in this unit mainly. Okay. So if you are again, so these are the topics now we are going to see that there is an importance and applications and what are the key challenges we are facing while they were calculating the strain energy. So you will see it in this session. So here if you are taking this, the importance, you can see this. So these are all the structures they have taken. These types of structures are subjected to the torsion. So this is structure, you can see this flyover. So while you are traveling the flyovers, you can see some slab will be there. That slab is, we are calling it a deck slab. Okay. So here in this deck slab, so this is we are calling it as a piers. Okay. Here there will be a twisting movements will be there. So while we were designing this piers, we have to take care of the torsion. Okay. And here this is the model which is taken from the software, and here we can compute the rotation under the tab. So here some softwares are available. You will do the manual design and analysis by using the structural analysis subject, and the same thing in software means we will use the StatPro or ANSYS. So many softwares are there, the analysis software are there. And also you can see this, these are the places where it is subjected to the shear. So if you are taking the earthquake forces, okay, so the earthquake forces is something but the lateral force. So once if the structure is like this, if the lateral forces are acting, this whole structure will get moved. It will create the shear. Okay, so here in that cases we have to take care. Okay, while we were designing the structure in the specific places, we have to take care of these types of loads. Okay. Here you can see this. So this is a model they have created, and this is a foundation and this is a column. When the earthquake forces are acting like this, you can see this how that the column got buckled. So we are calling this as something but the buckling. So if you are calculating the specific forces, okay, and then we can avoid these types of buckling of the columns. Okay, and next one we will see the derivation. Here the first one we have to take the torsion. So first for that we have to find the shear stress. The shear stress is nothing but force divided by area. So here the shear stress we can represent by tau b equal to TR divided by G. And what is the strain? We are representing by gamma. It is R theta by L. Okay. So here you know that Hooke's law. What is the Hooke's law? Elasticity is strain. So as similarly here if you are taking the rigidity modulus, here we are taking the shear stress and shear strain. So here we are in the assumption itself we have taken the shear stress is proportional to the shear strain. So if you are removing that proportionality, we are introducing a constant. That constant is the rigidity modulus. So therefore the tau is nothing but directly proportional to gamma. If the G is nothing but rigidity modulus, therefore from this we can get the twisting will be there. Okay, that twisting is represented by theta. Okay, and here if you are taking the J, that's a polar moment of inertia. Okay, so here this is the formula for finding the shear stress and shear strain. And if you are integrating everything, and finally you will get the equation for what tau max. Okay, so here you can see the what is the strain energy is represented by the formula U equal to T square L divided by 2G into G. T is the torque. So what is the torque? It is a moment. Okay, we will the unit for torque is Newton meter. Okay, it is nothing but a moment. Okay, and the L is the length of the shaft, and G is the rigidity modulus. J is the polar moment of inertia. So here, if it is calculating for a solid shaft, this will be the formula. If you are going for the hollow shaft, what are the two types of shafts we are studying? What is the hollow shaft? One is the solid circular shaft. Okay, so depending upon the whether it is a solid or circular, this formula will get varied. So now I think you have understood the concept of strain energy, how we have to calculate, and we will see the some challenges what we are facing. So when we are going for the complex geometry, so which means, so if it is a we are here, if I am taking this, so it is somewhat rectangle. So here if I am taking this, here it is a taper, and here some other dimension. Different geometry is involved. Here if I am taking some big structure, there will be the combination of all shapes will be there. Maybe rectangle, square, trapezoidal, everything. If you are finding the strain energy for such type of complex structures, then it will make some problems. It is very tedious. And next one is the material non-linearity, which means if I am taking this, here this chip is made up of different material, and this case is different, and this hook is different, everything is different. So here you can't say this, if you want to analyze this, it is a combination of different material. The material which is having the different properties. Okay, as like the structure also, it is a composite material. Okay, so if you are here, we are in RCC, we are using only the steel and concrete. But if I am going for the pre-stressed or precast structure, we are using different types of materials. Okay, then that means that will be the material non-linearity will be there. Okay, and next one is the multi-axial stress strains. So which means the axial load is nothing but if I am taking this, this is the compression member. If I am applying the load like this, we are calling that as a axial load. Okay, so here if the axial load is acting at one point, there won't be any problem. If it is acting in multiple points, then the calculation and the analysis somewhat difficult. Okay, and next one is a stress concentration. So which means if I am applying the load on this, if it is a load UDL, there will be the stress distribution will be even. If it is a UVL, the stress will be different in this place, where the places where maximum load is there, the stress will be more. So here the places where the stress concentration are happening, it is very difficult. Okay, and next one is a time dependent effects. What is a time dependent? Have you heard about the creep? So okay, so here if I am taking this, just imagine this elastic material. Okay, so if I am keeping some 10 kg weight, okay, if I am finding the reflection first day will be somewhat less. If I am finding after 10th day, that will be keep on the deflection will be there. So that means the creep. Okay, so here the time dependent, some properties are time dependent. It will be vary according to the time. If I am finding the n smallest, if I am finding first day, it is the same. If I am finding the 50th day, the same. Because if I am finding the creep, if I am applying load, so increasing the days, and then there will be the deflection will be increased. So the places where these types of time dependent parameters are making some problems on designing the structure. Okay, and dynamic loads. What is the dynamic loading? If I am applying the gradual load, it is different. If I am applying the loads, okay, well, it is not gradually increasing. That is a dynamic load. So mostly the earthquake is nothing but the dynamic load. In that places, the calculation is somewhat difficult, and the simulation accuracy, which means if you are designing an analysis any structure, we will make the small models. I think you have seen in some cinemas, some villains will make, they want to do the bomb blasting. What they will do? They will make a model, small model on the that building, and they will make the decision where they have to keep that bomb. Then how that whole structure will be get collapsed. So here same thing. If you want to make any structure, we have to model. Okay, we have to model in the system or also the some real, and we have to make the if the earthquake is applied, if you want to construct some building in some earthquake prone area, okay, if it is we are measuring that by Richters, okay, if it is some 8 or 7.5, same amount of load should be given in that model, and also in the software we have to give, and we have to check how it is getting safe. Okay, so for an example, if you want to design this, okay, some 1000 Newton is acting. Okay, I can't, every time I can't really apply and I can't design. So I will make the model on system and I will apply the load and I will see that what is the behavior, how it is behaving. So that's thing we are doing. But while we are taking the torsional load, the simulation is making somewhat difficult. Okay, so from this video, you can understand. So this is the assessment which is given for you. So I will post this question to your group. Okay, you can solve this by using the formula what we have seen, and you can find the answer also. Thank you, student, for listening the video. Thank you.